In this problem, we are looking at fundamental problem 6. We are skipping fundamental problem 5 for now because you are going to do it for homework, but you don't need to try doing fundamental problem 5 yet because it will make more sense after we do problem 6. Not fundamental problem 6, which we're looking at now, but regular problem 6, which we're going to be looking at later. So for fundamental problem 6, we have a particle traveling along a straight line with an acceleration of 10 minus 0.2 s meters per second, where s is measured in meters. So this s here is the position, it's not seconds. Determine the velocity of the particle when s is equal to 10 meters if the velocity is 5 meters per second when s is equal to 0. Okay, so we have acceleration as a function of position, which means, going back to what we had earlier, this came from equation 1, this came from equation 2, this is equation 3. If I have acceleration as a function of position and I'm not interested in anything with time in this problem, then I probably want to use equation 3. Although I would be able to solve the problem using equations 1 and 2 because equation 3 was derived from equations 1 and 2, so equation 3 isn't giving me any new information. However, it's going to be easier to solve just using equation 3. So I have, this is equation 12.3 on the equation sheet, A ds is equal to v dv. Now I'm looking for the velocity, so I'm going to have to integrate this equation here, and I'm going to take the acceleration that I have and I'm going to put that in to equation 3. This is a function of s. I'm integrating with respect to s. I have to figure out my limits of integration, but before I do that, let me put the v dv on the other side of the equation. So I could say I'm integrating from s1 to s2 and from v1 to v2, but for my lower limits of integration, I want to use the known quantities that they're giving me here. So when s is equal to 0, the velocity is equal to 5 meters per second. So the lower that limit that I use on the left-hand side of the equation has to agree with the lower limit that I use on the right-hand side of the equation. But because when we're at 5 meters per second, and I'm going to leave the units off there just for the sake of space. When we're at 5 meters per second, the position is 0. So at position 0, I'm at 5 meters per second. And then I'm looking for the velocity when the position is 10 meters. So if my upper limit of integration here is 10, then this upper limit here is going to be the velocity that I'm looking for. If you wanted to just keep the limits as s1 and s2 and v1 and v2, you could do that while you integrate and then put in the limits afterwards. I mean, put in the values that you have here afterwards. Okay, so then let's go ahead and integrate. So when I integrate 10 with respect to s, I just get 10s. When I integrate negative 0.2s with respect to s, I raise the power, divide by the new power, so that's negative 0.2 divided by 2, so that's negative 0.1 s squared. And then I have to evaluate from 0 to 10. And on the right-hand side of the equation, when I integrate v dv, we get 1/2 v squared. And then we're evaluating from 5 to v. So then I'm going to put in my limits of integration, and I have 10 times 10 when I put in the upper limit of integration there. So that's 100 minus 0.1 times s squared, where we're putting in 10 for s. So that's another 100. Then when I put in the lower limit of integration, I get 0 here, I get 0 here, so that's just 0, and I'm not going to bother writing that. Okay, then I put in the upper limit of integration here, which is going to be 1/2 b squared, minus the lower limit of integration, which is 1/2, and then 5 squared is 25. Let's see. On the left-hand side of the equation, we get 90. And on the right-hand side of the equation, I have 1/2 times b squared minus, I'm just going to leave it as 1/2 times 25. Maybe I wanted to pull the 1/2 out front. Let's do that. Okay, and then I can multiply both sides by 2, and I have 180 is equal to v squared minus 25. And then I can say v is equal to, bring the 25 over to the other side, we're going to take the square root, so this is 180 plus 25, but v squared was equal to 180 plus 25. V is equal to the square root of that, but v could be positive or negative, so we have to figure out the sign. You can do that on your calculator, and you should get 14.3, and the units for that would be meters per second. We're going to take care of that in a minute. Okay, so how do I know whether the velocity is positive or negative? If you go back and you look at the acceleration that they gave us, when s is equal to 0, the acceleration is equal to 10. And the acceleration is not going to become negative until after s is equal to 50. So when s is equal to 50, the acceleration is 0, then the acceleration becomes negative. And so if we go from 0 to 10 meters, then the acceleration is still going to be positive as long as this is the first time that we arrive at 10 meters, because if the acceleration becomes negative, let's say this is the positive direction. Your velocity is positive, so you're going this way. If the acceleration becomes 0, and then it becomes negative, then the object is going to start to slow down, and eventually, if the velocity becomes 0, the object will turn around and go back in the other direction, and then you'll be going this way, and you may hit 10 meters again. Okay, so assuming that this is the first time that we hit 10 meters, the acceleration is in the positive direction still, and the velocity was in the positive direction to begin with, so the object would be speeding up, and therefore this velocity would have the same sign as the 5 meters per second, so we're going to go with the positive sign there. So my final answer is positive 14.3 meters per second, and that concludes fundamental problem 6.